All right.
Okay.
So welcome to day 3, everyone. I'm Lucian Smith. I've been working with Herbert for several years, sort of on and off. My first project was to develop the antimony language from a previous version that Herbert had, and basically took that and made it modular, and that's become antimony. So today I'm going to take the first hour and talk about source control, and the second hour and talk about model databases and go through an exercise of pulling out a model and looking at it, just sort of give you the idea of what the process is to grab a model from somewhere and start to mess with it in using tellurium and antimony. So the first part might be review for people. If anyone regularly uses source control, feel free to tune me out if you want, but come back in at the next hour. But source control in general is going to be important. So let me start things up. There we go. All right. So a very basic introduction to source control. Source control is what you did, when you did it, and why you did it. There we go. So the source in source control is your source code, but in general, it's whatever it is that you're creating. You could be creating a program, you could be creating a document, you could be creating pictures, like whatever it is. If you want to control it or track and store how that modified with time, then you can use some sort of source control system. Basically, there's sort of like an iceberg effect here. There's the current version for your source. That's what you're using. But then underneath the waves are all the previous versions that you've been developing over time. And sometimes those versions can be really helpful in figuring out, first of all, in just tracking things, and so you know why you made decisions that you made. And also, like, if you end up making a mistake, you can go back and figure out when it was that you made the mistake and that sort of thing. There's several different options. I've listed SVN as the first one, even though that's probably not what you'll use. It's SVN, or Subversion, is solid. It's well used. It's older. And it can have problems merging. Like if one person tries to do one thing with the source and someone else tries to do something else with the source, and then you say okay, now we need to merge them back together and make one version. It doesn't do that quite as well as the next version, which is Git, which is basically taken over the source control world in 2022, and for the last few years as well. It's modern. It's way over designed. It's generally good with merging, and there's lots of support. My suggestion for you for using Git is that if you start looking things up, you'll find all sorts of weird things that you can do with it to do specific things, like, and none of it will make much sense. And you should ignore it all, because the more awkward things you can do with Git, the easier it is to shoot yourself in the foot. But basically, if you use Git sort of in a very standard way, and then just sort of give up and back out completely if something weird goes wrong, that should work for you. Mercurial is another option. It sort of has the same design as Git, and it came out sort of at the same time. But in the popularity race, Git won over Mercurial. The other type of source control is continuous source control. So if you think of Google Docs tracks each character that you type. And if you ever want to go back in time, you can look up your versions and figure out what things were in the past. It obviously doesn't have any problems with merging because it tracks everything everyone types instantly. So there never is a chance for anything to diverge and come back, which makes things a lot simpler. There's other places like Overleaf, which is sort of similar. It's not technically continuous, but it is pretty rapid, and again shared. Overleaf, I believe, uses Git in the background anyway. And if you want to, you can attach to that directly. Overleaf is a text doc-based system for creating documents, and it's very popular for writing scientific papers. And again, it's really useful because it tracks everything and everyone can use it once, and you can go back to previous versions and things like that. You can't, the only issue with the continuous tracking is that you can't make a change and then make some sort of comment about why you made that change. It's all just continuous changes. So for this, we'll use Git on github.com as an example. So GitHub is a very popular website that uses Git as a backend. But one of the main things that it helps with is it provides a whole interface for you to use the basic source control behind it. So I'm going to show you, I'm basically just going to look at a couple different source documents. There's sysbio, which is our lab's source control hub. And so that'll sort of give you an idea of what a lab's source control might look like. And then we can look at just mine and see the sorts of things that what a personal thing might look like too. Is there a dot? I don't know what your question. Oh, the recording light. I did, it asked me for when it was recording. It told me it was recording at the beginning. Is it actually recording now? Anyway. Okay, yeah, recording light.
Yeah, it is recording, yeah.
Okay, good. So the question, what does the back end mean? So it's basically, what I mean by back end is this. So there's the sort of the interface, which is just what your current version is. And then the back end is the thing that stores everything under all the previous versions, all the comments that you've made, everything else. And when we actually go to GitHub, we'll see some of those things. All right, so let me go to here, which I think will work. And I will stop sharing that screen and share a different screen. All right. Yeah, this is the right one. All right. So this is the GitHub page for the Sorrow Lab. You'll see we have 80 repositories, which is a lot. The two that are pinned here, sort of the main things that we provide access to for others is Tellurium and Roadrunner, which obviously you guys have been using a lot. But there's a lot of things that we've been working on as well. Herbert has been working on an Iridium simulator recently. VS Code Antimony is a project we've been working on to get antimony syntax and syntax highlighting and understanding and parsing and help with annotations into VS Code. So you can run VS Code, load up your antimony module and edit your antimony module in VS Code to help you make your model more easily. PhrasedML, well, actually, I think Veronica is going to be telling you a little bit about PhrasedML later. LibRoadrunner depths. So this is another thing you can do. So Roadrunner has different, as a source package, has different libraries that it depends on. And especially when there are multiple platforms that you want to have it run on, the main being like Linux, Macs, and Windows, the libraries it depends on then also have to work on all those platforms. And sometimes you'll need a particular version of it because they'll update something which will break your code. So you want to say, like, I want to use that old version until I account for the changes in it or something like that. So libRoadrunner depths just carries and links to all of the repositories and all the libraries that Roadrunner itself depends on. And I recently had to update it, and it was a pain to update, which means it would be even more of a pain if we didn't have something like that. So let me click on Roadrunner just to show you that. So this is our Roadrunner source. And when you go to any GitHub repository, you'll see something like this. This is this is the main directory where everything is. And then GitHub in particular will show you, I think here, let's see, there's going to be a file readme.md, and then this one actually like, so if you go to GitHub, it'll show you the readme.md file nicely formatted. Little summary, what it is, how you install it, whatever documentation. And this is entirely dependent on what the creator of the source code has put into their README. And then you forget about it and it goes out of date and you're like, oh crap, I need to update the README. So let's see. So like for Roadrunner in particular, the main source is in the source directory, oddly enough. And here you'll find all our different classes, all our different subclasses, all that sort of thing. And I don't need to go into that in particular. One interesting thing about this is that this is where you would find the history. So here, let me go back to just Roadrunner, just to make sure. So Roadrunner itself this is where you can see like how recently it was updated. This, I did a commit 12 days ago. There's a total of over almost between 5,000 and 6,000 commits. And then this little check mark means that it passed all the checks that we told GitHub to run. So I'm going to click on this and we'll see what's going on here. And then, so if you click on the history, it'll just show you everything that's been happening. And I've been the one that's been updating Roadrunner most recently. If you go back far enough, you'll start to see other people. Yeah, there's Claire was doing some updates back here. I am currently the person who's most likely updating Roadrunner, but in the past it's been different people. It was actually you'll see here, this is forked from Andy Smoji, SBML solver. He was the one that originally wrote the core code, and then he was actually working for Herbert at the time. We've developed it, and things have changed with time for that. So if you want to see what happened in a particular commit, you can click on that, and this will be like some random string, and it'll show you what we changed. And this was all, the CMake list is the build system. So I was trying to update the build system to get it to work. In this case, I think it was to get it to work on, well, this says Ubuntu manual build. So it wasn't working for me on Ubuntu when I manually built it. So I had to do some changes to get it to build again. And this shows you like, this is the bit I added, this is the bit I took out, this is the bit I added, etc. Let me go back to, oh, here we go. So I mentioned the little check mark. The check mark is when if you tell it to run things every time you check something in. That is invaluable, basically. Like if you have any sort of vaguely complicated anything, if you have checks that you run every time you check something in, it will tell you instantly if you've broken something. And that happens in particular if you're trying to build on different systems. I'll make a change because it works for me and because I happen to be developing on Windows, but I'll happen to break the Mac build and it'll just tell me like, nope, you broke something. Like, oh, okay. And then the instant I made the change that broke something, I can go change it, go look for it and figure out what happened. So from here, we can look at the details of that. So this shows you like all the different things that ran. The general sysbio Roadrunner thing ran. Mac build, several different Mac builds, several different mini Linux builds, Ubuntu builds, Windows builds. Let's go to some details. So let's see, this is still on GitHub. So this is GitHub's report that it got from our automatic running system. Can I get, oh, here we go. Yeah, okay, here we go. So the system that we use for Roadrunner is called Azure. So we have been working on with the Azure development to their system, which is a Microsoft One system, to build and run everything on all the different platforms. You can use GitHub Actions, it's called, also as a as a way that basically the same idea, but on GitHub itself. We used it because it was most convenient when we were looking into figuring out a system to use. And here you'll see, this is the general build. These are all the things that ran, and the nice green check marks means that everything was successful. If you click on a particular one, it'll give you the details of that. So we checked it out. We printed some variables because when things go wrong, you need to know like what the variables were. Some simple, basically background things. LLVM is the system we use to change a model code into computer bytecode. So that's obviously like the core. That's what makes Roadrunner go fast, is changing a model code into like just runnable code on your on a particular platform. Obviously, that has to work on multiple platforms because it will only run on the platform it compiles for. The core thing that actually checks the tests is the main thing I tend to use is to check if the configuration worked, if it built properly, if everything actually compiled, and then if my tests ran. Is this going to show me the actual tests here? There we go. So we run a wide number of tests. I guess this takes like 7 minutes to run everything after taking 33 minutes to just build everything. And it just goes through every piece of Roadrunner and says like, does this run? Does this run? Does this run? There's some, there's basically two kinds of testing that you will want on your project. One test is called a unit test, when you have a small thing and you have often just a function. I have a function, it's supposed to do this. And you test just that function. You give it input and you test its output. It's like, if I give it this input, does it give me the correct output? If I give it this other input, does that give me the correct output? You just run through that, because if you break that, that's really easy to say like, oh, this is where things went wrong. The other thing, type of thing you can check is sort of end-to-end tests. For Roadrunner, that would be like, I want to run a simulation. So I give it input that is just data, and then I do everything, which runs thousands of functions. And it gives me the output simulated data, and I check, is the output simulated data what I expect? If something goes wrong in that, it's harder to figure out what went wrong, but it's more likely to catch errors when something does go wrong. So sometimes like the individual functions work fine, but the way you're using them together is problematic, or one of your functions gives a different function like unexpected input that you haven't thought to test, and then something will go wrong because of that. And you're really only going to catch those sorts of errors in end-to-end tests. But you'll hear a lot about unit tests because those are the most powerful in terms of finding out quickly what went wrong. So yeah, we have basic things for Mac. Then we have different things for different versions of Python. This is the Python 3.8. And so we will compile it with Python 3.8, Python 3.9, Python 3.10. Because of the way things set up, we have to have different binaries for all three systems. So before we instituted the system, whenever we wanted to make a new release of Roadrunner, we had to find 3 different machines: a Windows machine, a Mac machine, and a Linux machine. We had to compile Roadrunner 3 times on each, one for like a previous version of like 2 versions of Python ago, the previous version of Python and the current version, then decide if we wanted to go even further back or like use the new experimental version. Compile, get everything together and send that all off to make a release. At this point, we have that all automated, and it's much, much easier to do releases and stuff. So I really can't overemphasize the ease of the easiness this thing will bring to your life. It can be a pain to set up, but it will save you so much time in the future. So let's see, where are we? Let me go. I said I would take you to the other, to like a personal account now too. Is that gonna work? All right. Let's do it. All right. So this is my personal GitHub account. Obviously, I don't have 80 repositories. I have a mere 10. And even that's a little high for a personal repository in my experience. It is generally things that I'm working on either on the side or like on as an experiment as I'm working on other things. I have some personal things on here. I have some work things on here. Several of these are forks. So a fork, I should explain, is when someone else has a GitHub repository and they're doing their thing and I want to experiment with it. All I have to do is then fork it. Basically I tell GitHub, I want a copy of that from myself that I can mess with that won't mess up anything for the person who originally owned it. They're like, great, here you go, here's a copy. So then anything I change there, and I don't even know if I made any changes here. Let me see if anything happened. I will look at the commits. So yeah, so like I forked things back here probably. So Stanley Gu was working on things for a while, and then I sort of was like, all right, I want to see, there's some things I want to change without messing with anything up there. So then I forked it and then made some changes myself. And I think at that point, then I like forked it back to the sysbio repository itself. And in fact, let's go sysbio, because I think we now have our own copy of SBMLint. Yeah, so the sysbio copy of SBMLint is also a fork from Stanley Gu. Stanley Gu was also the one who worked for us. He originally set things up in his own account, and then we sort of took over as the maintainer of that thing. So forks can become what is the main thing, even though it started off somewhere else. But GitHub itself is sort of agnostic on the idea. Let's see, what else? A few other things here. Cuner Python. So I worked with Dr. Cuner in her lab, and I had a bunch of Python scripts that I was using to run stuff, and I didn't want to lose any of them, and I wanted to make sure that if I changed things to where they stopped working, I could back up to where they were working again. So these are just a bunch of Python scripts that I was just using to manipulate basically one-off data. So even though all of this was mostly for a very single purpose that I wasn't really planning on using in the future, I still put it in a source code repository in order to save it and to make sure that I could keep track of how things changed with time. You can see I used it over a course of several years there. A amusing one is Cragney Manor. So Cragney Manor was a purely personal project. I was asked with a bunch of other people to create a room in a text adventure. And I was given like the name of a room and part of a puzzle that the users are going to solve, and then said, go for it. This is and a genre. And then so I could create everything in that room that I needed to do. And I was supposed to it was supposed to be a hidden library book in my room that people were supposed to find. And there were a bunch of library books in the game as sort of a side quest. So this is just my source code for that. It was an easy place to store it and update it. And again, like you will make mistakes and you will suddenly realize that you broke something several commits ago and wonder how that happened. And this is the way you can figure it out. This is the actual source code written in a language called Inform, which is written as natural language. So zoom in a little bit probably. So this is a description of a library book is usually a library book. That is actually source code for Inform. Anyway, so that's that. Finally, let's see if we can look at all the repositories because there's one in particular. So, oh, wait. So we're going to get to network modeling example. That's my exercise 2 for you all today. And I'm going to go back to my slides. That. This again. So overall, you can track, you can fix bugs. Oh, I forgot. That's a good, all right. You can auto test your code, you can record everything you did. And then one of the big things is actually like it's useful when it's just you, but it's very useful when you're working in concert with other people. Other people can then work on the same thing and not stomp on everyone else's work. The other thing is just that it's publicly available. Others can examine your code, others can fork your code and do their own thing. And they can submit bug reports and even fixes. And let me show you that part because I forgot. There we go. All right, we're going to go back to sysbio. And let's go to road. So the other thing that this is not specifically source control, but GitHub in particular, is that it will have an issue tracker for you. So here is issues. And anyone, like developers and people who are just using it, can file bug reports or comments or questions or anything else and say like, hey, this isn't working for me. What's going on? So I put this in here a little bit ago. So I say like, if a reaction rate is 0, it can't scale the control coefficient. So I filed that as a bug. I've fixed it a little bit. You'll see I mentioned that I fixed it in this. That's a reference to a particular commit. So you can click on this and say like, well, what did he do? And then this is what I did. I added this code, took some of this out, added a test. We're using a particular system called Google Test, but any system will work. So yeah. So you could, if you are interested in a particular issue, you can say like, all right, what happened? And if you are running into problems and Google your question, you will often find a link to some sort of issue tracker, and so where other people are discussing the bug. And hopefully the people are discussing the bug in the system where it can get fixed, and hopefully even further that it is discussed in a system where it actually was fixed. I will often find these sorts of discussions for someone having the same problem as I and something else. And so sometimes the fix that they made, I can also make the same fix. So it's really useful as just an information resource. And then it's useful for us just to keep track of what are all the problems that people are having with Roadrunner right now. How close are we to fixing them? How important are they? Is this just an enhancement, like a new feature that would be nice, or is this actually a bug that is causing problems for people? So that is the issue tracker. Are there any questions about any of that? Let me go back to this.
I have a small question about what you just said, that like you could go to other source codes and figure out the bugs that people have asked and the fixes. My question is, how do you know that those fixes have been incorporated in the source code? Like sometimes I, like, for example, work with a program and there are bugs like this, and sometimes you have to manually go under like a certain file and fix it manually yourself.
Oh yeah.
And sometimes it is incorporated in like a branch or like in some versions of the code. So how can you tell?
Yeah, how can you tell if a
looking
particular fix is in a particular thing?
Yeah.
That's a great question. Let me go back to this and we will sort of try to explore that. So here, this was the example. It was like, here's a thing, this is how it was fixed. Now typically like I would say GitHub usually relies on people being good about writing down what's happening in the issue tracker itself. So someone will say like, this is incorporated in release 1.2.3 or something. And it won't necessarily, and if no one actually takes the time to write that, then you won't know. But if they, and you all, like I had to put in this link to the source fix also, so otherwise you might not have known that. So let's see if we can figure out if this was incorporated in the most recent release. So this is the commit. That's one parent. And this is the branch that it's in, like, looks like. Develop, oh, and it has a tag, okay. So yes, it looks like for this is all tagged and it's all nice and it would tell you. So this tells you that it was, that fix was changed for version 2.2.2. And if you click on version 2.2.2, that was released 19 days ago with that particular commit. And then these are all the files that were there. So we were actually able to figure that out relatively easily. Now, again, a lot of that relies on people making those tags, making those releases, like putting a link in the issue tracker or something.
Oh, okay. So that so this means that if you see a tag in there, doesn't mean that that GitHub has realized that this has been incorporated. Someone has been like diligent enough to just put the tag in there for people to track it back.
Yeah, pretty
okay.
much. There's a reasonable amount of automatic things that happen, but not a lot. And so as people are getting better, I think, about utilizing GitHub. Let me see here. The other thing, if you know that if a particular piece of code, if you need a particular file in a particular directory, if you go to the code, you can look at the branches and say like, here, we're gonna go back to just Roadrunner. So here, we're just at the thing. Here's the source code. And right here tells you what branch you're on. So we make the develop branch the default, because that's what we commit to and uncommit from all the time. And then these are the other branches that we have. And I've been trying to be really good about, like, after we're done with the branch, I'll delete it. It for a while, like, our branch list was getting ridiculous. So we've been like 20 different branches long, most of which were not very useful. I think all of these are actually, at least technically, something we're actively working on right now. All that to say, this is the actual source that is the most recent thing. If you know that a file needs to be in a particular directory, you can just go to that file, say like, oh, it was in the source directory, it was in the LLVM directory, and it was the codegen base.h, and it was supposed to have the fix. Oh, and then this is the last commit that it was made for it, right? And then you can just click on it and look at it and say like, all right, go down to line 125, it's supposed to be this. Like, okay, good, it is. Or, oh, it's not, I'll need to make that change myself. Does that make sense?
Yeah, that answered even more than I expected. So thank you so much.
Okay, sure.
I really appreciate it.
Yeah. All right.
I have one other question.
Absolutely.
And that particularly refers to the fact that in your latest release, that was 19 days ago, so it's not too long ago.
Yeah.
And if we install with pip, we will install that version from 19 days ago, even though you have some changes and some comments from that time. Yeah. So the last comment in your GitHub is from 12 days ago. So there were some changes from the version we have.
Yes, exactly.
Pip, yes.
Right. And in fact, like, not only that, but like on Colab, you're using Python. Colab uses Python 3.7, and I didn't make if we look at the latest release. Okay, so that's another thing I didn't mention. But over here, you'll often see like the releases, and you can see the list of everything, previous one, previous to that, etc. So for 2.2.2, these are all the files, and you'll see that we have Python 3.10, Python 3.8, Python 3.9, but we don't have anything for Python 3.7 because at the time I didn't think anything you really used Python 3.7 anymore. And then it turned out like, oh, Colab still uses Python 3.7. Like, oh, okay, well. But there weren't any changes that we made that were critical since the previous one. So I think if I click on this, is that going to, yeah. So here's your Python 3.7 releases. And this was April, right? So that's not all that long ago. So the one you're using in Colab is from April. And again, because everything is automatically generated, we can actually come out with these releases a little bit more often than we used to. We used to sort of struggle to do 2 a year. And now I can do a couple in a month. If something's important, I can just say like, all right, here's all the files. I'll upload them to wherever they go. Usually pipe. So all these wheel files, WHL files, that's what I create to put on pypy.org, which is how you get, when you do a pip install, it grabs one of these files and gives them to you. And I have to have all of these different files in order for your specific operating system to have something that works for it.
Okay, thanks.
Yeah. Put it on. All right, I'm gonna go back to my slides real quick. Feel like I should probably just share my screen, but there's too many other things going on. So let me copy this into. So yes, so we're going to do an exercise. I'm going to have you create your own repository. Here's a document on how to do it, and I'm happy to walk people through it as well. So exercise 1 is to create your own repository. You might need to create an account on GitHub. That should be relatively straightforward. Pick a license, edit the README, make a new file in there, and then like commit it, and then try to and then look at the history and copy things back to Colab. I will copy this into. Into the chat. Oops. Also there. Bonk. Yeah, so there's your link. I'll give you, I don't, you know what, we have a little bit less time than I thought we might have. So I'm changing my mind. You can do that if you like, but we can also do exercise 2 at the same time. So exercise 2 is actually using source control a little bit to solve a puzzle. So I have this network modeling example where I checked in some code, I changed it over time, and at some point I messed things up. And your job is to figure out where I messed things up and to go back and figure out how to fix it. So here is this. I will share my screen again for this. And I think this exercise is actually listed on the network modeling example page also. So there is a single file there. Copy that into Colab after putting pip install tellurium at the top, and then you're going to have to look at the commit history and the different examples to find out what went wrong. Should we split into breakout rooms for that? Seem reasonable, Veronica?
You're the expert on GitHub. Maybe you should stay here in case somebody has a problem.
Sure. Yeah, I'll be in the main room. Feel free to talk about things as you go. Works. It's a good thing we were in a break. Oh, Veronica, yeah, okay. I see you. I had paused it once. Partway through, I was like, we're all doing nothing. I'll pause the recording. So.
Yeah, we were just talking about you mentioned this as well, Lucy, that GitHub is a bit over-engineered and a bit overkill, I think. It'd be nice if we had something specifically for modelers.
Yeah.
That was sort of stripped down. You had limited things you could do, but was still functional.
Right. Right. Well, I mean, in a way, that's the sort of thing that Overleaf did. Like, it uses GitHub in the back end,
right?
But it's stripped down for just creating papers, and it does just that pretty well. And the interface it provides for it is
something like that we need, for modeling.
Yeah.
Maybe that could be added onto the Visual Studio Code thing. Maybe.
Yeah, actually, I didn't mention that, but there are programming IDEs like Visual Studio or other things that have integrated source control in the IDE itself. It tracks if something's committed or not, and you just, without ever leaving your IDE, you can say like, yep, commit everything, here's my comment.
But maybe Visual Studio Code as is might be workable.
Yeah, could be.
Yeah, could be. Yeah, you want something that doesn't get in your way.
Right.
You just want to get on with the work rather than getting a PhD in Git studies.
Right. So there's a comment here.
Oh yeah, somebody mentioned this other thing which I'd heard of, but I don't know much about. Yeah, it's another sort of versioning system. Yeah, workspace. Yeah. Yeah.
So yeah, that's the basic idea behind source control. Hopefully you noticed where the mistake was, and if you were particularly clever, you could look at the commit message and figure out what it actually should have been. The commit message had it's like, I changed this number to this and this number to this, but I didn't actually change one of the numbers to that. I changed it to like 10 times that. So
what was the strategy? I mean, all I did was I did a sort of binary search until I found the place where it went wrong. Is that it?
That's exactly what you do. I mean, and someone else actually mentioned this in another room, is like, is there any faster way to do this? And if you have Git installed on your personal machine and a way, then that makes it pretty easy to say like, go to this version, go to this version. You'll have like a list of all the different versions. Like you just switch. So you can have your code up in one window, the list of commits in the other. You just like switch to this, run, it oscillates, switch to this, run, switch to this.
I can imagine, what would be useful is an application where show me the runs of all the models I've committed, or this range of models I've committed. And show me in a grid, and you can see then where the changes are, and then you click on that one and it brings it up.
Right.
Yeah, that'd be nice.
That'd be nice.
Yeah.
But yeah, I made that as an exercise just because I have literally done this several times. Like I've discovered something is wrong in the code, and if I go back far enough, it used to work, and I have no idea where it is. And literally I do binary searches, and I'll like write it out on a piece of paper because otherwise I get confused. I'm like, January 2nd, it worked. January 12th, it failed. January 10th, it did whatever. So it's not the most convenient thing, but there's nothing else like it. If that's the only thing that if that's the only way to find your problem, it's really useful, even if it's not the most convenient thing. Lab Notepad, ultimate version of a control tool. Yeah.
Oh yeah.
Yeah. All right.
Okay.
So let's move on to topic 2. Actually, let's give you a 5-minute break.
Okay. I'll have a look at Lab Notebook.
Sure. Do you want to start the recording thing? There you go. All right. Welcome to part 2. I'm going to talk a little bit about model repositories. And that's not what I want. There. I'm just going to all go from one window this time, so I don't have to keep switching back and forth. So model repositories. In general, they are a place that contain models. They're often SBML or CellML or other formats. Model repositories are places where, papers are like talk about models, but the model in those papers is often hard to get to, and the repository can be a place where it's just dedicated to just the models that you might publish things about. A curated repository is a place where people work for or volunteer for the repository itself. And as submissions come in, they say like, all right, and they look at the submissions and they make sure it matches the published paper or make sure it runs, those sorts of things, and then publish the results. They can also be non-curated. They can just be sort of open to the public, like throw your models here and we'll store them for you and we won't really look at them very much. Or they can be both. There are some repositories will have a curated branch and a non-curated branch. Different repositories have different purposes. often will be focused on a particular branch of research or science. And they'll just have models that are sort of concentrated, all the models that are like that in one place. Here are some model repositories. These slides are in the Google Drive, so you can get to all these if you like. These are just a selection of a few different ones. What I'm going to go into more detail today about is biomodels in particular. You can get there from biomodels.net, and that will redirect you to this EBI link. So I'm going to do that now. Oops. Biomodels.net. So here we see the basic thing. And again, like I mentioned there, I talked about a curated branch versus non-curated branch. Biomodels has a curated branch and a non-curated branch and an auto-generated branch. These are the three basic things that they have. The auto-generated branch tends to be ones that are models that are like whole gene, like the entire organism models, or like all of metabolism or something. And they'll sort of take a bunch of data, put everything together, call the resulting thing an SBML model. Often those are unparameterized, meaning that they don't have values for any of the parameters, but it'll say there is a K1 here and I don't know what the number is. Non-curated is a completely mixed bag. Some are great, some are very unfinished, just because they are just whatever state that the uploader is in. Often models start off in the non-curated branch and then they migrate to the manually curated branch over time. So the best models in biomodels are going to be in the manually curated branch. But if the particular topic that you're interested in ends up in the non-curated branch, you may be lucky, or you may get at least something to start on. So I'm going to click on the manually curated branch here, so we can look at things. There are currently over 1,000 models in the curated branch. And this is a list of them. You can search for particular models or topics or substrates or proteins or reactions or whatever you like in the search box to try to find out more. But let's just pick a random one here. So this is Biomodels 100. You can tell from the URL up here, or from here, I guess, the identifier. And this is the general, like what you'll see when you look at any of the biomodels. There's different tabs. This is the overview. This will tell you like the history. I've talked about like version control. Biomodels has a very basic version control. There's obviously just like 2 revisions here for this particular model. A lot of models will just have 1 revision. It's like, here it is. I curated the model. Here it is. This one, yeah, like originally this was uploaded in 2007. In 2014, they changed it slightly. So, so that is the version history of this model. It also gives you sort of an idea of what the timeline of these models are. As Herbert mentioned early on, that's one of the advantages of SBML, is that the model itself will still work, even though the software that was available in 2007 and the software that was available in 2014 and the software that's available in 2022 are all completely different from each other. You may not have any overlap between what was available then and what's available now, but the model itself should remain constant. Like, it is just a mathematical description of the relationships involved, and you can run it on any modern thing or any old thing. The files are where you will find the actual data. So here is the main file, the model file here, SBML level 2 version 1 representation of glycogen phosphorylase activation. And what's this preview thing? This preview thing will probably just show you the model. This is the actual XML of the model, which again is not super useful. It's probably not going to be very readable to anyone. But it is the file itself, and then you can just download it. So what I'm going to do, let me make sure this is exactly what I'm going to do Yes. So I'm just going to go through and using Colab and using biomodels, I'm going to find a model, I'm going to download it, and we're going to manipulate it some just to give you an idea of sort of how this process might happen. And then as an exercise, next, I will have you look for a model of your that you're interested in. So let's say that there is some sort of global health crisis going on, and you're like, are there any models out there that will help us with this global health crisis? So you type in your crisis here, zombies, and hit enter, and you find your models. Like, oh, thank goodness someone has modeled a zombie outbreak. So here we have 4 models. And we will, if you can see over here, that like 3 of them are in the non-curated branch and 1 of them is in the manually curated branch. So we know that manually curated branch has gone through at least some sort of revision where they like did some quality control. And that one, how could you tell? Let's see here. I guess we could just here, we'll click on manually created and then it'll filter it for just that one. So let's look at the zombie SIZRC model from Munes 2009. All right. So this is, so I've looked at this before. Sadly, if you actually like click on this link, it doesn't work. It's like, or, oh no, it does. It takes you to the whole book. It does works though. That's nice. I thought it didn't work. So let's use Google Scholar to actually find the, sure, why not? Scholar.google.com. We will delete publications and search for that. And there it is. We can get the PDF for us. So there's our source documentation, or the source paper. Everything that's in the curated branch of biomodels has a published paper related to it. And the model that's in biomodels is supposed to reproduce at least 1 figure from that paper. So looking through this, it looks like the basic model has 3 populations. You have the susceptible people like humans, like you and I, the zombies, and the removed or the dead. And so the basic model is shown here, like the SZR version, where the susceptibles can become zombies, the zombies can become dead, the dead can rise as zombies, and susceptible can just die straight also. They don't have to become zombies first. And there are all the different parameters for the rates at which all those different things can happen. So great, now we know the basic ideas. Let's go back, and this is in my way a little bit, but we'll look at here and see if we can get them all. So we're going to go to the files, and I could download the file, but I'm not going to because there's a faster way. Let me go to this. So biomodels, let me run this real quick. Sure, that's fine. I don't care. So the tellurium load s command will actually take a URL as input. So if I go here to the download link and right click and copy link address, then I can go here. Was this where I was? Nope, this is where I was. Paste it in there. And as soon as we're finished loading tellurium, then I should be able to load the model. I think, got it. So simulate it and plot it, and we'll see what happens. Look at that, there we are. I didn't, like I might have, one of the things I might have to do when I first download a model from biomodels is I might have to change my simulation parameters. 5 units turned out to be fine here. But sometimes you might, like nothing might happen. You might need to reduce that a lot, or you might have to increase it a lot. So great. Let's look at the antimony version of it. So we're going to print r.get money, oops. And there is the model. Dun, dun, dun. So again, this is sort of, it shows you like the compartments that we were mentioning earlier. Here's our reactions. And here's all our parameters and everything else. Also, people have mentioned a couple times like, hey, can I put in units? A lot of biomodels will have units, and this. So if you like load it into antimony, it'll show you how to do that. A unit is defined with the unit keyword. All of like liter, second, mole are all like predefined terms in antimony, so you can set the volume as a particular everything else. Obviously, everything in SBML comes with, especially in earlier versions of SBML, you had everything had a default unit. So zombies probably are not measured in moles, but that's how the model is set up right now. You can change that to be in like individuals or units or whatever. And then, yeah, display names, CV turns. We haven't talked a lot about this yet, but if you want to annotate your model and say like, this is a particular thing that came from this particular other thing, you can do that. These should be clickable. Let's see what the susceptible is. And it is the susceptibility term from what is this? Can't tell which, the NCIT ontology. So an ontology, we also haven't talked about ontologies. Ontologies are collections of precisely defined terms in different areas of science or anything that needs anything technical about it. So I don't remember what NCIT stands for, but it's probably about infectious diseases. And it is a property or attribute of susceptibility for that. And I would guess, hopefully, if we like removal instance, yeah, to take out of, that's the ontology term for that. So so obviously, like if we were looking at a biological model, you would click on something and it might take you to a description of the protein, or it might take you to a description of what glucose means, or what specifically we're talking about for that. We're not going to worry about that for this part. So we're just going to want to have the main model. So one thing you'll notice, and this happens with a lot of biomodels in particular, is that the rate at which things happen, which is a bit after the semicolon, is a function. Function for birth, function for zombification, function for susceptible to zombie or death, etc. And all these functions are translated into antimony as these function things up here, determined by the keyword function, just like model and end. So if you want to know what the rate is at which these things happen, you'll see that it happens. We hand in the parameters beta, susceptible, zombie, delta, and then we use this formula to determine the answer. Now, this is fine. It all works mathematically. It's not the easiest thing to read. And this is what, in particular, Coposi just does this by default for all of their models. They will always take any reaction rate that you put into any reaction, it will bundle it up as a function and save it as a function separately, which makes it a little harder to read when you're trying to just explore things. So I have, what do I have here? Here, because I think saved a little bit of code to do this more easily. All right. LibSBML. LibSBML is a library that works just with SBML models. Usually, you're not going to want to use it because it is designed for tools to use as opposed to being designed for humans to use. But humans can still use it. It's relatively, parts of it are relatively straightforward. So in this case, we're going to use libSBML to read it into a libSBML document and then create a converter, which SBML comes with, called expand function definitions. And the expand functions definitions will take what we just saw and just move everything to the reaction itself, so we don't have any more functions. So I'm going to copy this and go back to here. Oops, go back to here. And try to scroll down more. Back. All right, and paste in our little code here. So we imported the SBML. Hopefully it was installed. I think it was installed. And then this is the little expand function definitions and run everything else. And off we go. And so now our antimony actually, instead of having a bunch of functions at the top, just starts with the reactions. And now instead of now we can actually tell what's going on. Those are the reads. Oh, geez. Sorry. So there we are. Now let's do the reverse. Now we have this, and we're going to start messing with things. So we're going to copy it. There we go. And we're going to say the ant string equals this. And here, I'll actually stay here. R equals D load A and string, string, simulate, plot, just to make sure everything is still running as we expected. All right, so we're still getting the same thing. For the purposes of just messing with things, I don't want to have to be looking at all this annotation, so I'm just going to delete it all. If I can, control. So CV terms are gone, display names, units. I don't care that things are declared constant or not because we have antimony has reasonable defaults. And here we are. Also, we know that we don't really care about the compartments. The compartment is a default compartment of size 1. So we're just going to get rid of those. Donk. Donk. Make sure we're still running. Still ran, still doing exactly the same stuff. So now we can actually start to look at it's sort of simplified enough that we can start to actually reasonably look at things and figure out what's going on. So let's look at what happens. Birth, the creation of the new susceptible individual at a constant rate that is not dependent on anything. So that's an interesting thing, right? That like, oh, we're modeling birth as if birth just happened regardless of the size of the population. That's a reasonable assumption. It might not be the particular assumption we want, but now we can actually see what that assumption was, and it wasn't necessarily going to be obvious from the paper, as obvious as it would be from the actual from the model. So now we look at the next one, the zombification, and that is the creation of zombies from nothing. And instead, we have the creation of zombies from nothing, and we have the susceptible to zombie or death, the susceptible people or humans being removed from the population at two different things. So you'll notice this is basically just saying the rate at which zombies appear is this rate. And everything is sort of mixed up. That's not a very SBML-ish way of doing things. Because ideally what you would have is you would have actually what was in the paper here. You would have an S to Z reaction that happens at beta SZ. But we can at least see here that this is what the paper was talking about, and say nope. Yeah, here. At least we know beta times susceptible times zombie. That matches what was in the paper. Beta times susceptible times zombie, and the susceptibility to death or zombie, etc. Someone has a question. Easy way to check if a certain paper has uploaded a model to a repository. There, other than searching, no. Some journals, and we're getting slightly better about this, are require you to upload your model. and say like, all right, and then if you have that in your repository, then the paper will actually say this model was uploaded at such and such a place. Historically, though, that has lagged far behind what everyone else does, which is everyone just sort of publishes their model with their random code written in R or something, and then moves on with their life and loses their R code, and no one gets to use the model anymore. Biomodels started its life looking at old papers, recreating the model from scratch, and putting it up there for people as a public service. Yes. So let me finish talking about the previous one. So when the paper was published, there was no model in any model repository. And a few years later, some curators took it upon themselves to say, like, I think we should put this model in a repository, made the model, probably had to talk extensively with the original authors to say, like, hey, your paper doesn't say what half of your parameter values are. What are your half of your parameter values? And they will reply like, oh, a postdoc did that 2 years ago and they're gone and we have no idea, so you're gonna have to guess. Or whatever. It's just really hard to create models from old papers that don't come with models. And yeah, so the idea that, like, if you find a model, it's going to be a repository. Hopefully that will be changing more with time. Certainly if it's a famous model, that's more likely to have someone thought that, oh, we should put this in a repository. There are also certain subfields that are more likely and just have more of a culture of putting the models in repositories than others. I think that answers your question. Yes. r.getCurrentAntimony was indeed the code. I can show you that again. And this is again in the Google Drive. Yep, print r.getCurrentAntimony. So I loaded the model with TE load S because it was SBML into R, and then you can get current antimony. And then down here a little bit more, you can also get the current SBML, or just get SBML. And that's how I got it from Roadrunner to libSBML. libSBML converted it. libSBML wrote it back to a string. We loaded it into tellurium again, and then we printed get antimony. Oh, get current antimony or get antimony. Works for that. Right. So let's see here. So so last year was the first year I did this demo, and I found this model and I thought it would be amusing to work with it. But then the model really started to bug me because there's all these issues with it. And I swear I'm going to, like, one of these years, I'm going to just fix it all and resubmit it to Biomodel and say, like, here's a much better version. But for example, what we really want is birth is fine, but for zombification, what we want is susceptible to zombie at the rate of beta times susceptible times zombie. And the other thing you notice is that zombie is that typing susceptible a bunch of times is going to be really obnoxious. So that's what we would want for that. And then just normal death would be susceptible to removal at a rate of, let's see here, delta times susceptible looks like. Delta times susceptible. Susceptible is starting to look like a weird word to me now. And then zombie death as zombie to remove what, zeta alpha times zombie. Now ideally, and I think oh yeah, and then you want zombie death, and then you want death from zombie being to zombie, I think, right? No, susceptible to zombie is zombification. Death from zombie is susceptible. Oh, maybe that's not something that they modeled. Okay, here, let's go back here. So we should have 1, 2, besides birth, 1, 2, 3, 4 processes. Birth, 1, 2, 3, and there's one more, so I've missed one. Anyway, we need a zeta times removal. What's the zeta thing? Oh, that's like rising from the dead. Got it. So we want zombie roll to zombie at zeta times removal. So I'm going to hope that this, if I comment out these guys, that everything should be exactly the same as it was. Oh, look at that, I did it right. So I have now changed things to be more like understandable to me, and I'm still getting the same sort of results. So I think I haven't actually like messed with modeling ever. One of the things I then noticed from this is that the rate at which the dead rise as zombies is completely like a function of just the population of dead. So in this model, all dead rise as zombies at some point. So basically, this is no matter what you do with this model, there is a birth of susceptible people. They will die. They will rise as zombies. We will just get more zombies over time, and there's nothing you can do about it. And that's inherent in the model itself. And that's the sort of thing you can discover in once you actually like are looking at a model versus something you're not necessarily going to notice when you're just looking at the paper. There's a few more chat things. Let me. Susceptible to removal, zombies kill people. Yeah, I think there is. That's not how they modeled it, I think, right? Here in their model, there is a rate at which people die, but then there is a rate at which people just become zombies, and that is just based on that is sort of product activation in a sense here. The more zombies there are, the more you're going to create more zombies. The rate at which the dead rise as zombies is just a function of the population of the dead. The rate at which zombies die is a function of S, so like people can kill zombies, and there's more likely to kill them if there's more zombies around. And then there's just a rate at which people die of old age or other things that are non-zombie related. So yes, obviously, like you could make now you sort of understand the model enough to be like, oh, I could change this. Like I could make this a better model. Similarly, so they have other models here also. They're like, what if there's an infected stage? So you can become infected, and then there's an infected rate to zombies and dead. So maybe you're infected and you just die straight up, and things like that. And in fact, the label for this model on biomodels claimed that it was this model, and it just isn't. It's the SZR model. It's not the SIZR model. And I think, what do they have? They have a quarantine model also, where you try to like quarantine the infected and the zombies. They die at a certain rate, and now that would decrease the I and the Z values, which would decrease the rate at which S would go to I, etc. But effectively, since all dead rise as zombies, there's none of these things are going to help just based on the model itself. So, right, a person dies from a heart attack and becomes a zombie. That's just the way things happen in this model. So that's enough amusement for now. For the last 15 minutes, let me go back to my slides and ask you to search biomodels for a model related to your own interests. You could look at the other zombie models. You could find some COVID-19 models, which there are several now, or anything else, something related to your research or something else. Find the paper, look at the model in antimony, try to simplify the antimony, and try to play with it a little bit. We'll end the session with that. Give you 15 minutes to do that sort of thing. Feel free to break out into groups, and if you don't have a particular thing, maybe the leader can go through something if they would like to do that. Yeah, everything's being recorded, so you will be able to do that if you like. And not only the let's see. So the recording is available, but also everything is available on the Google Drive, and all the notebooks and the slides are all there as well. So models. Anything that's storable in SBML, it can. I don't know how many logical models are literally being stored in it. Oh wait. Okay. I will caveat that. There is a SBML extension called SBML qual. Just like you may recall, like distributions were sort of an add-on to SBML. Qual is also, or qualitative modeling is also an extension to SBML. And in qualitative modeling, basically, instead of a continuous value for anything, you have like states, or like things can take on like 2 or 4 values. It can be like 0 or 1, or 0, 1 or 2, or like blue and green, and those can be the 2 states or something. And you don't simulate them in the same way. You say like, okay, we're sort of taking a step forward, and the things are going to interact once, and then we'll take another step forward and we'll interact again based on just presence or absence of things. And Roadrunner doesn't do that kind of modeling. And antimony, I don't think covers that either. No, there's so the sad answer for that part is no. But there are SBML. You can still store them in SBML and move them among different groups. And in particular, there's something called Golomoto. And the Kawamoto group, I think, has a variety of software that you can use them all for logical modeling. And again, because they're stored in SBML, they can freely exchange the models, and you can robustly ensure that your model is the same among the different groups. Question: can libSBML be installed on personal Windows machines with pip install? Yes. You can.
Does it come with Tellurium? Does it come with Tellurium?
It comes with Tellurium, yeah, at this point.
So you can just go import libSBML.
Yeah.
I installed Tellurium on my computer, but it seems like it doesn't have that package added. It says there's no module called libSBML.
Oh.
Yeah, it's just, and I tried to install it using pip. It says we couldn't find a version that satisfies the requirement.
It is called python-libSBML. That is the, if you
I see.
Pip install python-libSBML, and then that's
okay, thank you.
But to import it though, to do the Python import, it's just libSBML.
Right, once you're in Python, but the name of the package is different. Sort of like,
Gotcha.
it's the same thing with Roadrunner, actually. You have to pip install libRoadrunner, because there's a different package called Roadrunner that has been non-maintained for 5 years and does something else completely different. So if you pip install libRoadrunner, then you'll get our Roadrunner, and then you just install Roadrunner. And if you want libSBML, you have to pip install python-libSBML. I'm pretty sure if it's not that, it's libSBML-python, but I think it's python libSBML.
Okay, so I just imported in Colab. I installed Tellurium, and I successfully imported libSBML.
Yeah,
it seems like there is a problem with my version, because I tried pip install python-libSBML, and it says it's already satisfied, but when I import it, it says no module named libSBML.
I mean,
so I think
here, this is on my screen. Look, so all I've done is installed Tellurium, pip install, and then I did import lib, libsml version 5.916.
Yeah.
So it
Yeah,
should
but
work.
that's Colab, right? It's not on
Right.
your personal PC.
Oh no, but if you pip install Tellurium on your personal PC, you should get the same thing should
Yeah.
happen.
The answer is it should work, and I'm sorry that it doesn't. And we could probably work with you to try to
Should
figure
work,
out what the
yeah.
problem
No,
is.
that's
Yeah,
probably
sorry.
a bad installation. I'm probably able to fix. I mean, again, I tried to install it. It says the requirements already met, so it should be
Yeah.
some sort of installation bug. So don't worry
Yeah,
about
probably.
it. I can take
Some things
it.
in
Thank
there.
you.
Oh, then,
Yeah,
there you
that
go.
makes sense.
So there's another package that we have called Simple SBML. So libSBML can be a little bit complicated for beginners. So there's another one called Simple SBML that sits on top of libSBML that in theory makes it much easier to access SBML from Python.
I mean, at this point, you can also just use Roadrunner's model building and modifying
true.
commands. You can add reactions. There are functions in Roadrunner itself where you can just say like add reaction, delete reaction, add compartment or whatever, ask questions about things. So some of those can also just be done there.
Yeah, here's the link to that.
Y'all can keep chatting, but just to not eat it too much into Joe's time, maybe we should like take a
Yep.
break. And if you want to keep chatting during that, that would be good.
Sure. Well, thank you all. Hope you enjoyed learning about zombies in SBML.